So today I'm going to focus on section 6.3, which is cubic models. And so I want to demonstrate for you example 6.8 before you do a homework question. So looking at the example, the first thing I want to point out before I even get started is there's a lot of words, there's a lot going on within this problem, and it's important to kind of take a step back and try to simplify it as much as possible to make it a little bit easier. So we'll talk about how to do that. The maximum theoretical power that can be generated by a wind turbine can be modeled by the function P equals, and there's the function. And notice as I go on that this is a cubic function because I do see V raised to the third power. Your two main variables that you'll end up with is the capital P and the capital V. And so just to recognize this is the cubic function, where P is the power in watts, A is the area swept by the turbine blades in meters squared, D is the air density in kilograms per meter cubed, and V is the wind speed in meters per second. Now, before I continue forward, let me just point out that I wrote the equation out, and for me, just writing the equation isn't enough. I want to identify in my own mind what these variables represent. So I did put P as power, A is area, D is air density, and V is wind speed. So that way, when I read a question and I'm trying to identify what either that they're giving me a piece of information or that I need to find a piece of information, I know exactly which variable I'm looking at. Okay. Now, the thing to point out next is reading that next part in this document. A certain wind turbine has a swept area of 80 meters squared. So they're giving me an A value of 80. Okay, and is located at sea level where the air density is 1.225. So notice again, they're giving me a D value. So I'm going to go ahead and substitute those values in for A and for D. And so for part A, to come up with that cubic model, I would say P is equal to 0.297 multiplied by that area they give me, which is 80, multiplied by that air density, which they give me 1.225, and then it's still a V cubed. So now what I need to do to kind of simplify this here, because this would not be your answer, but instead figure out using your calculator what 0.297 times 80 times 1.225. And don't just rely on me here. Go ahead, pause the video and multiply those three numbers together to convince yourself. So I'm getting P equals 29.1, and then that's V cubed. And so that would represent the cubic model for that wind turbine. Okay, so for part B, use your model to calculate the maximum theoretical power generated when the wind speed is 10 meters per second. So remember, wind speed is V. And so then they're giving me the wind speed of 10. So I'm going to take that same formula for part B and in place of the V, I'm going to replace a 10 in there. And so in my calculator, I'm going to punch in 29.1 times 10 cubed. Again, punch it in your calculator as well and see what you are getting for an answer. Okay, so I'm getting 29,100. And that's watts because we're talking about wind speed. I'm sorry, power. Not wind speed, that's power, P. Okay. And so then now for part C, they're saying, given that the wind speeds above 20 meters per second are strong enough to cause damage, give a reason why this turbine will not produce more than 300,000. And so what I would do is go back to this formula here, actually, where is it? Right here. And then I would plug in the 300,000 for P to essentially find V. So let's go ahead and do that. So P is equal to 29.1 V cubed. Plug in 300,000 watts for the P. Now, if I'm going to go ahead and solve for V, the first thing I would do is get rid of that 29.1. It is connected to the V cubed through multiplication. So I'm going to divide both sides by 29.1. Okay, and so then in that I'm going to get, and I'm going to need to round here, but I'll do 10,309. I rounded the nearest whole number equals V cubed. And then to find V, I'm going to need to find the cube root of that. And so just so you recognize, to find the cube root on your graphing calculator, you're going to need to hit the math button, and there's actually number 4 is the cube root. And then you can take the cube root of that number. And so I'm getting approximately 21.8. So again, I'll just jot this down so you can kind of see it, but I'm taking the cube root of that in order to solve this. So I'm getting, again, V equals 21.8. And I got to remind myself when I'm looking at that, that was in my original problem, meters per second. Okay, and then the last part is part D. Part D is talking about the reasonable domain for this model. And so if I think about this, starting at the low end of things, I think you can recognize when we talk about domain, and remember, domain are quote unquote the X values, range are your Y values. So we're looking at domain representing those wind speed possibilities. So on the low end of the wind speed possibilities, you could have 0. But then the upper end of that, and you got to kind of think about this for a second, is you have to think about what would be the upper end. And so when I take a look, we were told that wind speeds above 20 meters per second are strong enough to cause damage. So that could be considered the upper limit for that domain. It doesn't make sense to predict power for negative speeds. And so that's why I'm starting with 0. And so I would say something along the lines of 0 to 20. And so hopefully that helps you for this next homework assignment.